Before we start, I'll play a little tune, and you probably will recognize it. Listen to the words. So that roughly summarizes the opinion I hear from a lot of wireless LAN professionals whenever we start talking about IPv6. And indeed, IPv6 is chatty on the wireless LAN. And next hour, we'll spend talking about the reasons for this chattiness and how to manage as well this chattiness. And we will take a look at it from both the standards point of view and some of the Cisco-specific proprietary features that allow you to manage this. So in case you haven't guessed yet, I do work at Cisco. I actually ended up doing wireless not so long time ago, and I came from IPv6 side. Before that, I was doing a lot of network address translation, but then I did finally see the light and started to do IPv6. And I was doing a lot of IPv6 help to the wireless LAN professionals doing the conference setup. So that's the high-density deployments of, well, medium to large-ish size. So that's about 10,000 clients to 30,000 stations in the same wireless LAN. Now, my current day job is turning off IPv4 whenever I can and helping the customers to figure out the ways to do that. And today, I'm not going to talk about that, but I will talk about enabling IPv6 on the wireless LAN. And so we did enable IPv6 on the conferences for quite a while already. So it was probably, what, 6 years. And at first, it was very, very simple, because none of the devices supported that. So you enable IPv6, nothing happens, everyone is happy, everyone goes home. Now, somewhere in the middle of this path, it actually started to get used, and that's where we started to need to do all the tweaks that I'm going to talk about. But after we did the tweaks, and after we got the behavior on the wireless LANs back to acceptable, we wanted to see, so what exactly did we change? And why did the things start to behave better? So I will talk a little bit in two parts. So I will talk first about the reasons, well, how much is too much, and what's the impact of the excessive multicast on the battery life of the portable devices. And that's a little bit of a kind of small science project that we did with the graduate student in Paris who came from École Polytechnique, with whom we worked on this little project. And then after we see the impact of this, we will take a look at what exactly we optimize and what exactly we can optimize in IPv6 side to make the behavior better. So in order to understand how much is too much, really we took kind of a three-level model. So we first took just a simple device, a phone, and looked at how many packets does it send onto the network whenever it joins and whenever it stays connected. So just look at it from the pure layer 3 standpoint. Another dimension was taking a look at what does it mean a device gets the multicast packet. What does it mean for the battery, right? So pure 802.11 standpoint. What does it mean from the power consumption point of view? And finally, so these two vectors give us the behavior of the individual device related to multicast and the power consumption. But of course, the device doesn't live on the network alone. So we took the data from one of the real-world networks, and we combined that data with the behavior of the device to try to devise a somewhat an approximation of what the impact of many devices on the network is. So experimental measurements showed us that primarily the multicast happens in bursts whenever the device joins the network. So whenever the device connects, it needs to obtain the addresses, it needs to advertise the services that it offers, so there is a certain burst of 20 or something packets. Whenever the device just stays connected, the average number of packets is really pretty small. So that gave one interesting data point. So really, you can already see that, well, depending on the churn in the network, you will have more or less multicast in the network. Now, what does it look like from the 802.11 standpoint? A small refresher, well, DTIM interval. Who does not know what the DTIM interval is? So everyone knows, pretty much. So basically, every nth frame will be used to send the multicast information. So all the other frames, the device that is in energy-saving mode can be sleeping. So it can be awake only for a short period of time. Now, if the multicast is not buffered, then the device radio, and most of the portable devices actually have two processors, so they have the baseband and the CPU. And in this case, only the baseband has to be awake to just check, OK, we don't have the multicast bit set in the packet. We can go back to sleep. If the multicast was buffered, then the baseband needs to be awake for a longer period of time. And then, of course, to process that packet, the CPU needs to come to life and be awakened and to process that packet. What does it mean in terms of power consumption? So we took the phone, we ripped it apart, we connected the amp meter between the battery and the phone, and we measured the power consumption. So it turns out the difference between the mode, each subsequent mode, is roughly fourfold. So you start with 10 milliamps current whenever the device sleeps, 40 milliamps for the baseband, and when everything is up and running, it's about 150 milliamps. So this gives the rough understanding of what the power consumption for an individual multicast packet sent to the device. Now, let's superimpose that with the behavior from a real network. So that was a small conference network that we set up. It was just about 600 nodes. And by the way, later on when you get the presentation, you can take a look at the findings, so at all of this study in the internet draft that intern wrote. So we took the data about the session durations and the arrival times, and we plotted them. And interestingly, so arrival rates were distributed exponentially. So there was a lot of burstiness in this network, so a lot of flashiness. And that kind of is expected, right? It was a conference network, so much like you came from lunch almost all at once, or you went to lunch almost all at once, so that explains some of the burstiness. In other networks, probably the behavior will be slightly different. Now, connection durations. Interestingly, they were also distributed exponentially. So a lot of things in life are described by the exponential distribution, it turns out to be. The only kind of interesting thing was that they were not starting at 0. So this interval is actually 5 minutes. And our speculation was, because we don't have enough data to say 100%, but our speculation was that given that 5 minutes is the timer, idle timer for the session on the wireless LAN controller, probably most of the clients get their sessions disconnected while they are asleep, so while they don't disconnect the sessions fully, and some percentage of the clients do forcefully disconnect the session, or maybe switch to SSID. So using these values, we derived a model that allowed us to get so-called power multiplier. So how much more power does the device consume, given the number of nodes in the network? And with this network, even if we start with 27 nodes, that roughly doubles the power consumption compared to a single device on the network, if it just receives its own packets. So in other networks, it obviously will be something different, but would be interesting to hear your feedback as wireless LAN professionals in terms of how interesting this research would be. So I would be very interested to get in touch with you later on and discuss this. Now, that's kind of more theoretical mathematical model of the network, right? So we also wanted to go and just take a practical network and just take the packets, because packets don't lie. So we found, and it took a little while to find the network that doesn't have any of the vendor tricks that are applied to packets, but that was the network at IETF conference, which is basically a flat network with autonomous APs which don't have any IPv6 awareness. And protocols there were not tuned, so there was no configuration besides the defaults. And we sniffed the multicast packets. So a little quiz. What's the biggest contributor? Multicast DNS, absolutely correct. So multicast DNS takes about 49% of the multicast bandwidth. Now, the other large part is multicast neighbor solicitations. If you go further, so that's the Microsoft Service Discovery Protocol, then multicast router advertisements, and then finally multicast router solicitations and multicast neighbor advertisements. So service advertisements do take pretty much a lion's share of the bandwidth in multicast, but I'll push them to closer to the end of the talk, because service discovery is actually not something IPv6 specific. You have to manage that both on IPv4 and IPv6, because they're sent typically on both of the protocols. And instead, we'll talk about two functions, neighbor maintenance and the router discovery. And those two functions are performed by part of the IPv6 protocol that is called neighbor discovery. And by the way, quick question, how many of you run IPv6 in their network? Okay, so about 10 people. How many people studied IPv6 or ran it in the lab? Okay, another 10 people. So for those of you who haven't started, actually, a few slides earlier, there was at one of the early slides, there was a link at the bottom, which is a link to a very interesting book about IPv6, which describes IPv6 from the standpoint of IPv4 professional. So it takes IPv4 state of the art, and then it shows which problems IPv6 was supposed to solve with that. So I found that pretty unique, well, besides being free to download and being available in English and Russian, because it was written by a Russian speaker, and that was not me. It's interesting that it explains the whys of the protocol, right? Because a lot of books just go and tell you, okay, this is this header, this is this field, this is used for something, but you don't know why this header appeared, or why a particular header disappeared from IPv4 to, when moving to IPv6. So that book, it gives you a very unique perspective in understanding why, and that's the most important part. So neighbor maintenance, that part really is very similar to IPv4. That is basically a different naming for what you know as ARP. And in IPv6, neighbor discovery, so the neighbor maintenance works over ICMP version 6, as opposed to separate Ethernet protocol. Router discovery is something new. So that is something that actually was standardized for IPv4 as well, but it never got implemented because it got too late. Because DHCP in IPv4 is the protocol that is used to discover the router. How do you discover the router? You type it into the DHCP server, then the DHCP server tells to your hosts where the router is. In IPv6, that's a separate part of the protocol, and it is kind of independent. So you cannot tell from the DHCP server, this is the router. So the router discovery is an integral part of IPv6 protocol, but it is separate from assignment of address. So let's talk about the neighbor maintenance. And if we go into the neighbor solicitation that constitutes most of the neighbor maintenance, we see that majority of the traffic, well, sort of unsurprisingly, is neighbor solicitation of the hosts sending to the routers and of the routers sending for the hosts. So that's hosts and router trying to resolve each other's addresses. Then a much smaller percentage is the duplicate address detection, which is used to probe whether the address is used before using it. And just between the hosts. So remember, that network was a flat network, so the host could communicate directly. Now, this part actually consists of two parts, as we kind of speculate, because again, in this case, we had collected the data, but we didn't have enough way to probe that live. So that's a little bit of the post-speculation, and that's based on the way the IPv6 neighbor discovery state machine works. So whenever you need to resolve an entry from layer 3 to layer 2, right? Like you have the in ARP in IPv4. First thing you do is you create the entry in the incomplete state, and you send a neighbor solicitation, which is similar. It's a brother of IPv4 ARP request. And that gets sent to multicast. When you receive the reply from the host that has that address, you populate the entry, and you write the Ethernet address of the target into that entry, and you can start sending the traffic. Right? So that's basically how ARP works pretty much in IPv4 on the basic level. Right? So you send the request, you receive the reply, you populate the entry, you use it. Now, in IPv6, I mentioned that the router discovery mechanism is separate and is more flexible compared to IPv4. So what happens if you have multiple routers? You somehow need to figure out which of the routers to use. Right? And this necessitates as well the mechanism to know when the router is reachable, when the router is not reachable. Because if you just start to send the packets to each of the routers, that's not nice. So this resulted in an addition of the neighbor unreachability detection mechanism into the neighbor discovery in IPv6, which actually also, if you look closely at the behavior of the IPv4 stacks, this similar mechanism got backported into IPv4 as well. So what happens is that this entry stays in reachable time, in reachable state, but at the time the entry is created, a timer is started called reachable time, and when it expires, the entry is translated into stale state. What does that mean? That means that we are no longer sure whether we can have bidirectional reachability with this neighbor or not. When we have the traffic that uses this entry, we shortly keep it in the delay state. And the reason for that, because that's another optimization, if we have two hosts on the same segment that communicate, then we might use, for example, TCP between the two hosts. And if we send SYN and we get back the SYNAC, then we have the confirmation from the upper layer protocol that there is bidirectional reachability. Right? So then we can shortcut the entry directly into reachable state again. But in practical scenarios, most of the time, you have router and the host talking. So when there is no confirmation from the upper level protocol or no upper level protocol between the two devices, we send unicast neighbor solicitation. And when we receive the reply, we put the entry into reachable state back again. So in effect, every active neighbor entry kind of cycles through this circle. And if you see on the router, you will see that some entries will be in the reachable state, some entries will be in the stale state. Now, effectively, that means that you have kind of a, well, it's neighbor solicitation, neighbor advertisement, but it's kind of almost like a ping request response, right? Per device, per active state entry. So what's the value of this timer? The timer is set based on the base reachable time, which is received either in the router advertisement packet from the router or is taken as a default. And the value is in milliseconds, and I put it in bold because that's fairly important whenever if you or someone else gets to configure it in the router, that's one of the few values that is in milliseconds. A lot of them are in seconds. We take that base reachable time and throw a dice and pick a random value between half and 1.5 of it. And every few hours, or when we reconnect, we pick another random value. So why do we do that? To ensure that there is no synchronization between different hosts on the same segment. So we want to ensure that all these probes are distributed. Now, how big is this base reachable time? The default value is 30 seconds. So that means that for every active entry in your network, for every active neighbor entry, there is an ICMP traffic between every 15 and every 45 seconds. So that's quite a lot of probe traffic. So that's one of the sources of chattiness of IPv6, where you have this ICMP background neighbor unreachability detection going on. Now, of course, that is a unicast traffic, right? But wireless networks are very volatile, right? You may have 100% coverage, you may not have 100% coverage. So whenever the neighbor unreachability detection fails, then the entry is essentially deleted, and the probes fall back to multicast. So that is something we believe in that particular network caused this huge amount of multicast neighbor solicitations being sent. That was very busy radio and not so optimal radio conditions. So that was a lot of neighbor entries falling back to multicast probing. Now, what can you do about this? Well, as I said, primarily the interesting part for this neighbor unreachability detection is to find the router that is no longer reachable and to fall back to another router. But this was designed back pretty much almost 20 years ago, right? So in the meantime, we have protocols like HSRP, VRRP, which allow you to have one virtual router, which just takes over in case one physical router dies. So you can simply increase the reachable time, and this is the Cisco CLI, but every other router vendor will have the CLI to tweak this value. And because in this case, you don't really care whether the router is reachable or not. If the router is not reachable and you have 10,000 clients, you will know very quickly. So you need to bring this value up, right? And the safe default to start with is 600 seconds, and again, this value is in milliseconds, right? So if you put it in seconds, it will hurt quite a lot, because you just reduced it instead of increasing it. So then this value will be sent in the next router advertisements to all the clients, and the clients will kind of calm down, and they will consider the router to be reachable, and they will not probe the router anymore. So that will reduce the amount of traffic. And I was talking about the multicast probing. Worst case scenario, which actually happened in a couple of anecdotal stories that I was not involved in, is that the router crashed. So you have thousands of clients that are connected, and then the router becomes unreachable. So then the neighbor unreachability detection fails on all 10,000 clients at the same time, and then they all start sending multicast. That hurts quite a lot. And that hurts not even on the wireless, but on the wired side as well, so on the router. So that's why setting these to a higher value is simply a matter of precaution as well. Now, of course, you need to manage the wired side router neighbor cache as well. So depending on the parameters on the scale of the box, you might want to time them out a bit sooner sometimes or not. So before we move to router discovery, what questions do you have about neighbor maintenance?
So what you're saying, layer 1 design matters?
Layer 1 design absolutely matters, because having perfect coverage is great, and everything would work if you have perfect coverage and perfectly behaving clients. But there is absolutely the kind of abstraction leakage between the layer 1, layer 2, and layer 3. So let's talk about router discovery. So in this pie chart, actually router discovery is not that huge of a part. But in real life, a lot of times, well, you can actually get rid of these packets here by, as I said, by good radio design for good coverage. And as well, I will talk about it later on in the presentation. Depending on the setup, you can actually eliminate most of these packets. So these packets will constitute quite a significant chunk of the traffic. Now, to see what those packets look like, we'll take a look at the process of the IPv6 host getting online. So before, and here, before I go into discussion, here I'm looking at the setup from the layer 3 standpoint. So that's why the first step is the layer 2 link comes up, and I realize that's a bit of a dangerous thing to do at the wireless LAN conferences, to represent the link coming up with just a single line appearing between those two hosts. Yes, but it's magic. And the first thing whenever the link comes up, the host configures IPv6 link local address. So every host that has an interface that is IPv6 enabled, and pretty much all the hosts have these interfaces these days, they will have IPv6 link local address configured on it. But also, as part of IPv6 standard, before using any IPv6 address, the host has to check whether this address is used already by someone or not. How does it do that? It simply sends a request for this address into the network and sees if there is anyone replying to that. So pretty much like you do the duplicate address detection in IPv4, right? You send the ARP. If there is someone replying to that, cool. That means, or rather uncool, because this address exists already. So same thing happens in IPv6. The neighbor solicitation goes on the link, and if there is no reply, then the host starts to use this link local address. So now we have a link local address. We can use that to source another packet called router solicitation. What does this packet do? Well, I was saying about the router discovery in IPv6, which is a separate mechanism, right? So it's not part of any configuration protocol, but it is a separate automatic mechanism for router discovery. So routers actually periodically send packets called router advertisements. So they advertise their presence on the wire. Obviously, you don't want to send those too often. But what does the new incoming client do? Does it have to wait until the next router advertisement is sent? No. It sends a router solicitation to all routers multicast address, which then triggers the routers on the link to send router advertisements ahead of time. And what do these router advertisements contain? They contain configuration, well, besides of the fact of the presence of the router on the link, they also contain some configuration parameters. And that's where it gets quite interesting in terms of new stuff, because one and primary interesting parameter is the prefixes that this router serves on the link. Besides just the value of the prefix, it also has the flag which tells the host, hey, you can use this prefix to automatically configure your address. So then the host can take the 64 bits of the prefix, so the upper 64 bits, and generate, by whatever algorithm it chooses, the lower 64 bits, and then declare this an address that it will use. Because the router has promised that it will route the upper 64 bits. So then the host has simply to choose whatever lower 64 bits that are not yet used on the link, and it will verify that by doing another duplicate address detection process. And once there's no one using that, the host is free to use that. So really, you see that that's one of the kind of new things with IPv6, where the host can be free to choose its own address. Even though it is not really that new, because if you don't have any DHCP server on the link, your IPv4 address will be 169.254.something.something. So it's, in a way, it's kind of similar process, except instead of 169.254, the router can assign the prefix that is routable. Is that enough? For dual stack hosts, that can be enough. But for pure IPv6 only host, what do we miss in this case? DNS, absolutely right. So there are two ways to do DNS. And the one I show here is the so-called other configuration flag, which instructs the host to obtain the configuration from the DHCP server. The nice part about this exchange is that it's completely stateless. So the DHCP server, which sits either on the router or somewhere, doesn't need to store any state, because the state primarily is the address information of the host, which the host did by itself. So this part can be done statelessly. Can we do the stateful assignment of address on the host? Yes, we can. There is another flag which is called managed address configuration flag. If it is set in the router advertisement, then this triggers the host to do a stateful DHCPv6 exchange and obtain the address and, of course, verify its uniqueness. So one thing about these 4 boxes here, if both of the flags are set, then it's obviously a single DHCP exchange, so both configuration and the address are sent within the same packets. What happens if you have both auto-configuration and managed flags being set? Well, the host will acquire both temporary address or Slack address and DHCP-v6 address. So that will result in 2 addresses being assigned to the host. Now, what are the multicast packets in this case? So first of all, router solicitations. Right? So the router solicitation is a trigger to all routers. So it doesn't need to be sent into the air to all the hosts because, well, normally on the wireless network, you don't have the routers within the stations, right? So you don't have the uplink being wireless, being a wireless station. So for that reason, the router solicitations, unless the wireless device is something very, very simple and just bridges all the packets, they are typically not sent on the wireless. Now, the neighbor solicitation packets, it will depend. So in the wireless LAN controller case, actually, it is behaving fairly smart, and it knows about the neighbor discovery process being done by the host. So it actually is smart enough to not forward all these extra neighbor solicitations onto all the clients. So that part, and that's the part where I was talking about this large segment of neighbor solicitation. That part is largely dampened by the neighbor discovery proxy on the wireless LAN controller. Finally, the only part that remains from all of this process is the router advertisements. And remember, I told you that even though on the pie chart, in a flat, simple, stupid network, it looks pretty small, in a large-scale network with all the wireless LAN controller features and with all the wireless LAN controller features, it's actually a significant part. Now, why is it a significant part? So the IPv6 RFCs were actually written quite a while ago. What was the prevalent media back then? Thick coax, right? If I send the packet down the thick coax, it's pretty cheap to send unicast or multicast. It's actually no difference, right? Because everyone on that bus will read the packet to some extent and will see, well, that's not for me, I've read it, but I'll discard it. So getting multicast was not much more expensive compared to unicast. So that's why in the protocol specification, actually it was written, hey, well, while you are sending the packet, you might as well refresh all of the timers on all of the hosts. So normally, the usual case will be to multicast this packet. You can still may choose to unicast, but there's no point in doing so, right? Because the host will have to discard this packet. If you connect another host, you will have to send another unicast, so don't do that. Well, that's all the 20-year-old network with big mainframes, big machines connected to thick coax. They don't join and leave the network very often. If you take a conference setup, what happens there? Well, you can see yourself. It's actually quite a few packets coming in. Right? So the multicast router advertisements get sent pretty much every 3 seconds, which is the maximum, well, minimum allowed time between the router advertisements. If there was no this safeguard, then it would be, based on the distribution we saw earlier, probably the interval would be even shorter. So now, these router advertisements are sent multicast on the wired side. The controller can either send it multicast over the air, but then it triggers a lot of other things, like the fact that multicast packets are sent differently compared to unicast, right? So there is different methods for that. So what quite a few vendors choose, including Cisco with wireless LAN controller, they actually send the router advertisements unicast over the air to each client. So this solves part of the problems with multicast distribution, and also this creates other problems, because if you send one packet to all the hosts every 3 seconds in the network, well, that creates a lot of contention in the air. But the plus side is that all of these packets are acknowledged, so we don't have to send them every 3 seconds. So we can send them much less frequently, because for each packet that we send to the host, we get back the ACK. So as a result, we can throttle them on the wireless LAN controller. So we can say, hey, you know what? I can allow only 10 router advertisements in 10 minutes, and no more. And then wireless LAN controller will look at the number of router advertisements that pass through. And once it reaches 10, within the interval of 10 minutes, it's not going to send through any more router advertisements. So it will calm the air quite a lot. Now, of course, well, the clients that connect, they want to get their router advertisements. So if they just have to wait 10 minutes, that kind of defeats the whole purpose of router solicitation, router advertisement exchange. So in order to help with that, as part of the implementation, the wireless LAN controller also checks which of the clients have just sent router solicitation. So which of the clients really want to get the router advertisement. And for those clients, it converts the router advertisements to unicast and just sends them to only those clients. So as a result, when the client comes up, it still gets router advertisement, but everyone else doesn't. So that, of course, reduces the usage of airtime dramatically. Now, if we are throttling the router advertisements, and this value is, well, that's one of the example values, but really I usually put it even higher, you might want to take a look from the IPv6 standpoint and look at raising the lifetimes as well. Because if you send the router advertisements infrequently, well, you might be better off in increasing the lifetimes. And in the slides at the very end, there is an example configuration from one of the conferences that we did where actually the lifetimes for the prefix are just set to infinite. So for router, there is an upper limit of 9,000 seconds, which is set in the standard. So you cannot set it more than 9,000. And for not really any good reason other than IPv4 router advertisement standard had the 9,000 seconds, which never got implemented. So of course, this is kind of a tricky scenario, right? So the router first sends multicast router advertisements, then the wireless LAN controller has to figure out which ones to send, which ones to not send. So it seems sort of obvious that within 20 years, we should have figured out a better way. Well, so yeah, so after 20 years, there is a better way, and that's just router sending the solicited router advertisements unicast. So that's a separate command that you would put in, and then the router would send periodic router advertisements via multicast, and the solicited router advertisements would go unicast. So this is something that is not prohibited by the standard, but it took a while to actually get to this because, well, no one really needed this on wired. So it never was implemented. And, well, it's also, well, as far as I know, it's implemented in Cisco iOS, but I don't know if other router vendors do implement that. If they don't, and you use other router vendor, well, then tell them. Now, if you use old version of the Cisco iOS, then there is a kind of a hack that you can use in the very dynamic environments, which is not to send the periodic router advertisements altogether, which is not very nice, because your maximum connection time will be limited to 2.5 hours. But still, it may be better, because especially now, primarily, you have dual-stack networks. So IPv6 networks are relatively rare with Wi-Fi. So for the time being, well, if you have the emergency situation, that can be something that is helpful. And that's something that we used a couple of times. Of course, all of this experience, well, it would be a shame not to take it back to the creators of IPv6. So a couple of references that you might find interesting on the ongoing work that we are doing in IETF to make IPv6 a bit more friendly to low power, to Wi-Fi, to all the, well, IoT-like environments. And, well, some of them have become RFCs already, so this RFC 7559 is about having the initial router solicitation being sent more resiliently. And then there are a few more. So this, remember I was talking about the limit of 9,000. So this actual limit, once I started to dig into that, there's no good reason why it cannot be 65,000. So that's the document that will raise this value in the standard. So then even the workaround approach will give approximately, well, almost half a day of the uptime, which for the dynamic environments is going to be more than enough. And a couple of other things. So this is a draft we are working on with Lorenzo Caliti from Google, who works on the Android side of things, who do see this problem with excessive router advertisements quite acutely. And actually, some handset vendors, seeing a lot of router advertisements, they say, you know what? We'll just block IPv6 altogether when the phone is off. So this results in better battery lifetime, but this results in inability to receive the notifications when the phone is off, right? And you generally would like to have your phone ring whenever you have an incoming message. So that's a draft which talks about the better configuration for the networks and better configurations for the routers, and discourages the handset vendors from dropping the router advertisements on IPv6 traffic. Questions about the neighbor discovery? Everyone's asleep. Service discovery traffic. So as I said, it's really not IPv6 specific. Service discovery typically runs on top of, well, it's multicast or broadcast rather in IPv4 as well. So the methods that you use to deal with that in IPv6 are exactly the same methods that you use to deal with that in IPv4. And while talking wireless LAN controller specific, well, you can use Bonjour gateway, so you can segment the MDNS traffic to different AP groups. Then, more specifically for the large-scale setups, depending on the setup, you can either block the service discovery with the access lists, so if you still need the multicast traffic for some other reasons. You might block peer-to-peer traffic, so you block the traffic between the clients. And finally, well, you can disable multicast altogether with kind of a question, well, with the asterisk. I will return to that a little bit later. So peer-to-peer blocking, well, very simple. Of course, you all know that it blocks the communication directly from client to client, right? So whenever the packet gets to the access point, it doesn't get sent to another client. But there is a small twist related to this. So in IPv4, whenever you block the peer-to-peer traffic, normal IPv4 stack will not communicate with another client in the same subnet. In IPv6, there is a knob that can allow you to actually bounce that traffic off the router, if you wish to do so. So besides the various flags that I was talking about, so that's autonomous address configuration flag that I was talking about for automatic address assignment by the client, there is also a flag which is called onLink. What does this mean? So if this flag is set, and it's set by default, then the determination of the address being of the host being onLink or not is the same as in IPv4. So if the host is within this prefix, then it's onLink, so we just send the neighbor solicitation, we do the neighbor discovery with that host. If the flag is not set, then we do something more interesting. So if the flag is not set, then on the host, you'll see that it does not install the directly connected route for the directly connected prefix. So as a result, your host becomes connected kind of via a point-to-point link to the router. So anything that is not addressed to the host itself goes to the default gateway. So that gives a few interesting possibilities. A, well, even if you block the direct communication between the hosts, you can still allow them to bounce the traffic off the router, and you can control the traffic on the router, besides being able to control the traffic on the wireless LAN controller. So then you have 2 points to enforce which traffic you allow, which can be nice if the people managing the router are not the same people as managing the wireless infrastructure. And another part of this, because you're punting all the traffic to the router, then this device, if it is a little phone that you have in your hand, it doesn't have to maintain as many neighbor entries. So it can communicate with a lot of hosts, but in the case of large-scale install, it can be 10,000 clients on the same prefix. So it can communicate with pretty much any client on that prefix, but it doesn't have to maintain any neighbor entries. And that is something that we've seen in these large-scale setups. When we first started, we did not clear the on-link bit, and actually did cause some interesting bugs with the clients when they blew up their neighbor cache, right? So when they had too many entries. So, and that's probably, potentially that may be also some interesting setting for the future IoT setup as well, because then again, the client will just know about the existence of the default gateway, and it will send all the traffic to default gateway. And if it needs to communicate with another IoT device, it will do so with the help of the router.
Do you have any numbers on when you blow the cache?
So it was again a bit of a hard to get a grip on it, because it's primarily, well, battle scars. So when you experience that, then you just try to clear it out. So to get it off, and when you have this many clients, so I don't have any exact numbers. So that's something that probably is worth testing and submitting the bug reports, but I never got around to that. And a couple of configurations. So for the router, how do you configure that? You set the keyword which specifies that the prefix is off-link, and then you add the route explicitly on the router itself, so that it knows that it does have to do the neighbor discovery for all the clients. So this kind of configuration will cause effectively all the communication to traverse the router. And you can see here that as well, I increased the reachable time, and I also have increased, well, I also have custom lifetimes for the prefix, so that's where they are configured.
Yeah, I had a question on that. You said, does it bounce off the router, or does it go in and then back through after it goes through its ACLs?
Yep.
Yeah, so it actually
goes all the way up to here. Then you can have the access list. I just didn't add them here to not blow up the slide too much, but you can have an inbound access list on the router, and then the router will U-turn the traffic and send it back to the client. And there is another part in that, well, at least in the protocol part, where the router can also send a redirect to the client and say, hey, well, you know what, Keith, next time when you talk, you use directly the direct connection. You do the neighbor discovery. So I can send an IPv6 redirect. Now, I was talking about disabling multicast. So actually, even though IPv6 does use fundamentally a lot of multicast, so in the specific case of the wireless LAN controller, you do not have to enable multicast on the controller if you just, all you have is just basic IPv6 connectivity. So that's a critical part, because kind of intuitively it seems, well, if IPv6 uses multicast, we need to enable multicast. So when you enable multicast, that also, of course, causes all the wonderful service discovery protocols to pop out of the closet, and you need to fight them. If you don't need to run service discovery, then you can keep this checkbox off, and you still will be able to get IPv6 connectivity. So the proxying part in the controller will do pretty much the same thing as is done for IPv4 in pretty much all the wireless vendors, right? So IPv4 also has lots of these chattiness issues. It's just that they have been there for 20 years, so we don't even notice them, but a lot of ARP, a lot of traffic is being proxied on the controller. And another part, while talking about this proxying, is that controller also tracks the addresses assigned to the clients, both v4 and v6. And I've been talking about the neighbor discovery protocol. So controller uses the snooping of this neighbor discovery protocol to populate the table, which tells which client has which address on which VLAN. And then how can it verify? It can send the DAD probe, so the duplicate address detection probe, to the client in the table, and if the client still has the address, it will reply with the neighbor advertisement, so that confirms the existence of the address on the client. If the client does not reply with this neighbor advertisement, then the controller can delete the entry. So as a result, the controller has always up-to-date information which client has which address. So this way, one client cannot spoof the address of another client. And in order to understand a little bit better of the configuration parameters of this mechanism, there's really, a simplified state diagram of the entries in this table. So whenever the new entry is added, it goes into reachable state. It stays in this state for the duration of the configurable parameter. Then, when this timer expires, it goes into stale state, and again stays in this state for as long as it is configured. And once that timer expires, which is a fairly long one, it goes back into reachable state to verify the, so it does the verification of the host reachability and goes back to reachable state if this host is reachable. Now, why do we have these two states, and why do we verify the reachability, and why is this timer longer? So the reachable state means that the entry is in the table and cannot be deleted. The stale state means, in this context, that the entry in the table may be re-verified and deleted if we are going with too many addresses on the host. So an example of that is iOS device. So how many people in the room have iOS or macOS 10 device? So probably about, 60–70%. So if you use the stateless address auto configuration, so the mechanism where the device itself assigns the address, then each time you reconnect to the Wi-Fi, your iPhone will assign itself a new address, which is fantastic for privacy from the user standpoint. But then from the Wi-Fi standpoint, it's kind of a little bit of a nuisance. So the wireless LAN controller has the hard-coded limit of 8 addresses per host. And whenever the host starts to recycle the addresses very fast, then it looks at the addresses in the stale state and tries to verify to see, well, hey, if you have so many addresses, probably you are not using some of them. So it verifies them and deletes if the host is not using them. If the host uses more than 8 addresses, well, tough luck, so that's not going to work. So, and finally, these are the defaults, and despite the fact that they are changeable, you don't really need to change them. So they're there for very corner cases with some strange devices, but really in the practical experience, we've seen that these defaults work pretty well. And you can see that, as I said, reachable lifetime is very short, whereas the stale lifetime is very long. So the entries stay in this table for a very long time. If there is a data traffic, then the controller pre-creates an entry, and this is just an example from the CLI. So it creates an entry, in the incomplete state. As I said, the state diagram was a little bit simplified. And it then verifies that the host does indeed have this address. So if someone wants to spoof some random addresses, they will have to do a little bit more work. They will have to implement the entire IPv6 stack. And once the wireless LAN controller confirms the reachability of the address, it puts the entry into reachable state, and then it starts to pass traffic through this. So, to summarize, I believe in this session I showed to you, what are the various contributors to multicast on the wireless LAN, and I think by now you should have understanding of how you can manage them in your installations. And one kind of cautionary note is that, the big impact that I was talking about starts in the networks from maybe 300–400 nodes in the same segment. Right? So if you have the networks that is below 300–500 nodes, then really you don't even have to touch much. So the amount of chatter there is minimal. It's not enough to cause significantly big problems. So that's all I had. Thank you very much.
Any questions for Andrew?
Yeah.
So you mentioned like 300, 400, 500 nodes. Presuming that's like with the default settings, that's when the chattiness starts to go up and it starts to hit the airtime. Is that kind of where you're going?
Yeah.
So this sounds weird because I don't know V6 very well at all, but in the same way one might have been trying to contain broadcast segments in V4 in, say, a building and have, you know, I don't know, /23s or lower than /22s. And I think, I can't remember, but /64 is like the smallest prefix you can use. I'm just thinking about sizing or designing for a campus. How you, apart from tweaking the timers, is there anything else you do from like an address schema?
So you can partition based on the areas. But from the addressing standpoint, you always assign /64s. So really, that's another part which is different in IPv6 compared to IPv4, is that you don't think in terms of how many hosts I put on this segment. You think in terms of, OK, where do I allocate the prefixes? So you just put /64 everywhere, and then this frees you from the necessity to do too much subnetting, right? So you still have to do the address planning, but it's more address planning in terms of subnets. And well, so on that topic as well, though, there are ongoing discussions about, say, hey, you know what, there are hosts that don't do DHCPv6, for example, Android devices, right? So what about if we just give /64 per host, and then just let them take whatever addresses they want, and then that's kind of also similar to the way IPv4 addressing is done. Because in IPv4, you kind of manage the individual address, and in this case, you will manage the individual prefix per device. But that's not yet in any, well, Wi-Fi deployments that I know. So it is really pretty much the default modus operandi in 3G environments, right? In 3G, 4G, the devices may get /64. They use slightly different mechanisms, but they might get the whole prefix for themselves. And potentially that might actually leak into Wi-Fi with all the convergences between the cell and Wi-Fi. So that may be something that happens in the future.
So then, from what you said, potentially should I be looking at, say, like a VLAN across, say, 3 floors for X number of people, and then give that a /64 prefix, and then break out the VLAN based? So
that will depend, because I'd say from the troubleshooting simplicity standpoint, you'd be better off, well, if you have the gear that can do this, like, well, I do know that you have WLC, right? So it may be simpler to just put them into single /64, because then you don't have to hunt down the whole question of mobility, where which VLAN this client was originally in, and so on and so forth. So that's going to be simpler from the troubleshooting standpoint. And that's the big reason why we do, in the large venues, the large single segment, because that simplifies things greatly from the troubleshooting standpoint. Because even having to narrow down which AP the client is on, that's already, if that's something specific to AP, that's one degree of freedom. And having to deal as well with different prefixes, that makes it harder. So I would just say, if you have a larger network, then you might as well just turn on all the optimizations, and then you'll be better off. Yeah, so you can Google IPv6 for IPv4 experts. Yeah, so it was on the slide. I'll see. But just searching gets faster. Link, yeah, so that's, gets here, yeah. So the URL is a bit long, but you can search in Google for IPv6 for IPv4 experts, and that will get you to the book. Yeah.
Do you see many client-side bugs still? Obviously, in the early days, whenever that was 5+ years ago, let's say, when it started to become more common, you know, there was probably more. But do you still see today problems, not even bugs, just implementation lacking? You mentioned Android not supporting DHCP. Are there still many?
Yeah, so Android not supporting DHCP, that's kind of, well, that's one would almost argue it as a feature. But that's primarily, that's not really a bug, that's the decision that they made so far. And the bug for DHCP v6 support was, well, at present it is closed. In terms of bugs on the clients as such, I think we've seen, well, I haven't really seen IPv6 specific bugs, well, beyond the handsets dropping IPv6, right? So that was that's probably one of the kind of more prominent things that I've seen. But I also have seen good news. Just a couple of days ago, I got an email from someone who updated the handset to the newest version, and that problem actually got fixed. So that's one of the reasons why we had this internet draft is, and Lorenzo actually wrote a patch which he sent to the vendor, which does router advertisement processing in the baseband processor. So it deduplicates router advertisements in the baseband. So then you saw the power consumption, kind of the staircase, right? So it's 10, 40, 150. So then you can stay within this 40 milliamps instead of going to whole 150 milliamps, and that kind of makes life better. And then, of course, well, all the operational considerations that we're trying to advertise a bit wider, that, well, you should not multicast router advertisements too frequently.